Hey guys, welcome back. So today's topic is linearization. This is where we are going to use linear functions to approximate values of an unknown function. So we'll use the equation of the tangent line, and we're going to use the derivative, the slope of the tangent line, all that kind of stuff. We're going to put this in point slope form. So this will be very similar to when we wrote the equations of the tangent line back in units 2 and 3 as part of our derivative questions. Only now, instead of just simply writing the equation line, we're using it to predict a certain value. Now, the linear approximations are not going to necessarily be the most accurate approximations simply because if the function is anything really bizarre, beyond that point of tangency, it's going to start getting way away from the tangent line. Better approximations we'll talk about in Unit 10 with the idea of Maclaurin and Taylor series. But for right now, we're just going to see with the linearization linear function. So make sure you're comfortable with your point slope form equation, y minus y1 equals m times x minus x1. Now that m is the slope, the tangent line. Now, because these are approximations, these are estimates, they are not going to be exact. They will either be over or under estimates. How we'll know? Well, it depends entirely on whether or not the second derivative is positive or negative. If the second derivative is positive, this value will always be an underestimate. If the second derivative is negative, then this value will always be an overestimate. Now, they will either come out and tell you directly that the second derivative is positive or negative. They may not come out directly, but they'll give you the function. You can find the second derivative and plug in the value and see whether or not we're positive or negative. Or they'll talk about the idea of concavity. And we haven't really discussed concavity yet. That's something we'll discuss with part of the graphs in Unit 5. But concavity is the main concept referring to the second derivative. So if something is concave up, that means the second derivative is positive. If something is concave down, that means the second derivative is negative. All right, so those are the three different ways they'll talk about. You'll be able to know whether it's an over or underestimate. They'll tell you directly second derivative is positive. They'll tell you directly second derivative is negative. They'll tell you concave up or concave down, or you'll have enough information from the original function to take a second derivative and substitute in and see, do I have a positive or negative value? Okay, so if you look at this first example, they tell us the function is concave up on its domain. So this tells us that since it's concave up, we know it's automatically going to be an underestimate, 100%. They give us the value of the function f of 4 is equal to 5. They give us the value of the derivative at 4 is equal to 3. And they want to know what is an estimate of f of 3.8. So we use our linear approximation. And they'll tell us, again, using local linear approximation for f at x equals 4. So we set up our y minus y1. So there's x1, there's y1. So it's y minus 5 equals, and then there's m, the 3, the value of the second derivative at this 4. So 3 times x minus 4. Now they want us to find the estimate for f of 3.8, so we can substitute 3.8 into this right here. So we have 3 times 3.8 minus 4. So we have 3 times a negative 0.2, which can give us a negative 0.6. We add 5 to that. We get 4.4, so f of 3.8 would be approximately 4.4, and this would be an underestimate. All right, so that's how we're handling this question. We're just writing the linear equation based off the information, using the value of the function to fill in the x and y coordinate points, and the value of the derivative to fill in the slope, calculating the answer, and substituting the value they want us to approximate, the 3.8. And again, recognizing because it was concave up, that meant it was an underestimate. All right, so here they want to know what is the estimate for f of 1.1 using the local linear approximation for f of x, given negative 2x cubed plus 5x minus 1 at x equals 1. So we don't have our coordinate point yet, so we have to find that. So we got to find f of 1. F of 1 would be negative 2 times 1 cubed plus 5 times 1 minus 2. So it would be negative 2 plus 5 minus 2, which is 1. So our point is 1, 1. Our slope, we need the derivative at 1. So our derivative function would be a negative 6x squared plus 5. So our derivative at 1 is negative 6 times 1 squared plus 5, which is negative 1. So our slope is negative 1. And we need to, well, we're going to need to do an over or under estimate, so we're going to have to go ahead and find our second derivative. So second derivative would be a negative 12x. Second derivative at 1 is a negative 12. So that tells us we're going to have an overestimate because the second derivative is negative. All right, so using our information, we're filling our according point. So it's y minus 1 equals negative 1 times x minus 1. We're going to fill in the 1.1 in for x. And we're going to use that to approximate. So we get 1.1 minus 1, which is 0.1, times negative 1 is negative 0.1. Adding the 1 over, we get a positive 0.9. So f of 1.1 is approximately 0.9. And again, this is an overestimate. So that's all we're doing from giving you the information based off a function, giving you function values, all that kind of stuff. And again, if we have to actually calculate the value of the function, value of the first derivative, value of the second derivative, to go with, to get the coordinate point, to get the slope, and to get the over-under estimates, then we will. That's all we're doing for that kind of stuff there. Now, you might also get this in what's called a differential equation. So we're going to talk more about differential equations in Unit 7, but a differential equation in its most basic form is an equation of derivatives. So dy dx, there's our derivative, equals e to the y, 2x squared minus 5x. Y is the function f of x. It's the particular solution for the differential equation. It has initial condition f of 2 equals 0. We want to estimate what f of 2.2 is. So we will discuss how to actually get and solve this differential equation, get an actual equation, y equals kind of thing. We're not there yet. Again, that's part of Unit 7, but we can use all the information we need because, again, we're given the x1, y1. Our slope is the value of the derivative. They don't tell us it directly, but they do give us the information to plug into the derivative. Dy dx at this 0, 2, or 2, 0, sorry. That would equal e to the 0 times 2 squared minus 5 times 2. E to the 0 is 1. We get 8 minus 10. So our derivative is negative 2, and that's our slope. So we go ahead and set up our tangent line. So it's y minus 0 equals negative 2 times x minus 2. So y would just equal negative 2, and then we fill in the 2.2 for x. We get negative 2 times 0.2. So negative 2 times 0.2 is going to give us a negative 0.4. So f of 2.2 is approximately negative 0.4. And notice they don't ask about whether it's an over or an underestimate. So we don't have to worry about doing that type of analysis. All right, so only worry about over and under if they actually ask for it. We also really can't, again, with our current knowledge, figure out what the second derivative is going to be for this anyway. Again, how we get that from that differential, we can talk about that. Well, I guess we could kind of. We've talked about implicit derivatives, what this would turn into. But again, overly tedious, not necessary. They don't want that. So in addition to a differential equation, they also give it to you based off a table of values. So this is kind of similar to example 1, only it's more in a table format. So they want to find this approximation of g using the linear approximation at 4. So again, they give us our x1 value, they give us our y1 value. Our slope is g prime at 4, which is this number right here, the negative 1.1 from the table. The rest of the stuff is just extra information that's not necessary, especially the 4.1 stuff. We really want to make sure we ignore that because we're not using 4.1, we're using the approximation at 4 to estimate the value at 4.1. So it's our y minus y equals m times x minus our x value. So that becomes y plus 1. Again, we fill in our 4.1, the one that we're trying to approximate. So we get negative 1.1 times 0.1. So we multiply negative 1.1 times 0.1. We're going to get negative 0.11, so 0.11. Subtract the 1 over. Y is a negative 1.11. So our g, not f, g at 4.1 is approximately negative 1.1. And again, we don't know anything about the second derivative, so we cannot make an assumption based off whether or not this is an over or an under estimate. All right, so that's our linearization technique. You're writing just linear equations, so you just need a point and slope, and then you're going to fill in a value for x to approximate a value that you're looking for. All right. So that's it for linearization. Only one more topic left to go. What's called L'Hopital's rule. It allows us to work with limits that are indeterminates. We discussed a little bit of that back in Unit 1. We're going to discuss it a bit more. So I'll see you next time for that.